So imagine this. You've built the perfect algorithmic trading strategy. I mean, you've got your higher time frame entry logic, your dynamic stop losses, take profit thresholds. It's a standard 12-parameter setup.
Right. Pretty typical for a robust strategy.
Yeah, exactly. The architecture is flawless. But, unless you tune those 12 variables to their absolute optimal configuration, the strategy just bleeds alpha.
Oh, absolutely. It leaves money on the table.
Right. So you want to find the perfect settings. And let's say your computer is fast, like you can test one combination per second.
Which is incredibly fast, by the way.
Right. So you hit start. And to test every single combination, your computer will finish the job in exactly 8,950 years.
It's just wild to think about.
It is. You literally would have had to start your backtest around the time of the Neolithic Revolution, like right when humans were figuring out how to farm wheat, just to have the results ready for today's market open.
And that's assuming the computer never crashes.
Right. So welcome to the deep dive. Today, we are tackling the, honestly, maddening invisible walls of algorithmic optimization.
It's a huge issue for anyone in quantitative finance.
Yeah, because how do you find the mathematically optimal settings without waiting 9 millennia? I mean, it's an infrastructure problem, it's a calculus problem, and ultimately, it's a map-making problem. Okay, let's unpack this.
Yeah, the time frame you just mentioned really highlights the ultimate trap, right? Especially for anyone stepping into complex data science.
Because we all think computers are just infinitely fast now.
Exactly. We operate under this assumption that compute is cheap and, like you said, effectively infinite. We think we can just brute force reality.
Just throw more hardware at it.
Right, but mathematics imposes a very strict speed limit on brute force. It's known as the curse of dimensionality.
The curse of dimensionality. Sounds ominous.
It really is, because if you don't intimately understand that the topology, like the literal shape of the mathematical space you're trying to search, you'll just crash into that wall at 1,000,000 miles an hour.
Completely blind to the fact that there are better ways, which is the core mission of our deep dive today. We're navigating the math, the psychological illusions, and the programmatic solutions for hyperparameter optimization.
And we're relying on a really fantastic, highly technical blog post for this.
Yeah, it's by an author named Sunat, titled Coordinate Descent versus Bayesian Optimization, which finds better parameters. And it is remarkably thorough.
It's basically a masterclass. It explains why brute force is a literal impossibility and why the most popular shortcut that traders use...
Oh, the shortcut everyone uses.
Right, the shortcut that systematically blinds them to optimal profits.
Yeah, and then it gets into how we deploy Bayesian probability models to find the absolute peak of a multidimensional mountain in like 8 minutes instead of 9,000 years.
And what's great is that the author grounds all this theoretical math in actual executable trading architecture.
Right, so we're moving from the naive approach of checking every box to deploying AI that maps multidimensional spaces probabilistically. So to really appreciate the Bayesian solution, I feel like we first need to autopsy the brute force failure.
We do. We need to look at exhaustive search, which the industry calls grid search.
Right, grid search, where you just build a matrix of every possible parameter value and force the CPU to evaluate every single coordinate.
Every single one. And on a micro scale, I mean, this actually works.
Right, like if we had just 2 parameters, say an RSI, look-back period, and, I don't know, a static stop loss.
Perfect example. And we want to test 9 values for each.
So 9 times 9 is 81.
81 runs. The CPU calculates 81 iterations in the time it takes you to blink. It's nothing.
So you add a third parameter, also with 9 possible values.
Right, so that pushes us to 9 to the power of 3, 729 runs.
Which is still, completely trivial for modern hardware. You run the script, go get a coffee, and it's done before you sit down.
Exactly. But the scaling here isn't linear, it's exponential. The mathematical notation is big O of n to the power of k.
Where n is the number of values being tested.
Right. Yep. And k is the number of parameters.
Okay, so our real-world scenario involves 12 parameters. 9 values tested across 12 parameters is 9 to the 12th power.
Which is a massive number.
Yeah, the source text gives us the exact integer. It is 282,429,536,482 billion.
And that explosion right there, that volume, that's the curse of dimensionality in action.
It just scales out of control instantly.
Because when you add a new parameter, you aren't just adding a new column to a spreadsheet, you're adding an entirely new spatial dimension to the search landscape.
Wow.
So the volume of that space grows so rapidly that the available data becomes sparse and exhaustive search just becomes computationally impossible.
Let's contextualize that with actual hardware limits, though, because a backtest isn't just a simple arithmetic operation, right?
Oh, not at all. It requires the engine to step through historical price data, calculate technical indicators.
Simulate order fills, track the equity curves over time. It's heavy.
Very heavy. Even if you have a highly optimized execution environment in, say, Python or C++A, where a single full history backtest takes exactly 1 second.
Which, by the way, is aggressively fast.
Extremely fast. But even then, 282 billion seconds equates to that 8,950 years.
And if you add just one more parameter, like say you introduce a dynamic trailing stop.
Oh, then you go to 9 to the 13th power. Your processing time jumps from 8,950 years to over 80,000 years.
That is just nuts.
It is. You could string together a cluster of the fastest GPUs on the planet, parallelize the workload across a massive Kubernetes cluster, and you are still waiting centuries.
You literally cannot throw hardware at an exponential math problem.
You really can't. Though the author does explore hardware optimization a bit, specifically touching on pre-computation using a Parquet cache.
Right, because the logic is, if we can't reduce the number of runs, can we drastically reduce the time per run?
Which is a crucial step for any quantitative workflow, to be fair.
Yeah.
I mean, most amateur backtesting engines, they load CSV files row by row.
Yeah, they read the timestamp, the open, high, low, close, the volume.
They load it all into RAM and then calculate the indicators on the fly for every single test.
Which has to be disastrously inefficient.
It's terrible because the CPU spends most of its clock cycles just waiting for data to move from the hard drive to memory. It's an I/O bottleneck.
Right, but Parquet is different. It's a columnar storage format.
Exactly. Meaning if the strategy only needs to evaluate the closing price and, say, a pre-calculated moving average, it only pulls those specific columns into the CPU cache.
It completely bypasses that bottleneck.
Yep. The author's previous work actually focuses heavily on generating these cached data frames. You pre-calculate all your indicators, all your time frame aggregations, and serialize them into Parquet.
And the text says this optimization can take a backtest from 1 second down to 0.1 seconds, right?
Yes. A tenfold increase in execution speed.
Which is a phenomenal engineering achievement. But against the curse of dimensionality, it's literally a drop in the ocean.
It really is.
Because at 0.1 seconds per run, that 12-parameter grid search drops from 8,950 years to 895 years.
Right. We've moved from the Neolithic era to the Middle Ages.
Still completely useless for a trader who needs to deploy the strategy by Monday morning.
Exactly. That mathematical wall forces a compromise. If we absolutely cannot test the entire grid, we have to sample it.
We need a shortcut.
Right. And human intuition naturally gravitates toward the simplest possible sampling method. The industry refers to it as an OAT sweep, standing for one at a time.
Okay, let's dissect the mechanics of OAT, because I think it reveals a massive psychological blind spot.
It definitely does.
So in an OAT sweep, you take your 12 parameters and you isolate the first one.
Right. You hold the remaining 11 parameters completely static at some predetermined default value.
Okay, so you iterate through the 9 potential values for parameter 1. You find the value that gives the highest P&L, and you lock it in.
Then you move to parameter 2. You leave parameter 1 locked at its newly discovered optimum. You leave parameters 3 through 12 frozen at their defaults, and you test the 9 values for parameter 2.
You find the best one, lock it in, and just march sequentially down the line until you've optimized all 12.
Yes. It's a single linear pass through all the variables.
And the computational savings here are just staggering. Like, instead of n to the power of k, the complexity becomes big O of k times n.
Right, addition instead of multiplication, essentially. 12 parameters multiplied by 9 values is just 108 runs.
We collapsed 282 billion iterations down to 108.
From 9,000 years down to roughly 11 seconds.
The appeal is totally irresistible. I get why everyone does it.
Oh, absolutely. And there is a slightly more robust variant of it called coordinate descent.
How does that differ?
Well, in coordinate descent, you acknowledge that by the time you optimize parameter 12, the overall mathematical environment has shifted.
Right, because the optimum you found for parameter 1 way back at the beginning was based on default values that aren't there anymore.
Exactly. So you run the OAT sweep again. You perform these multi-pass sweeps until the values stop changing, until the algorithm converges.
So you loop through the 12 parameters, maybe 3, 4, or 5 times, until the outputs stabilize.
Yeah, so you might run 500 tests instead of 100, still infinitely faster than grid search.
But, and here's where it gets really interesting, the author explicitly warns that both OAT and coordinate descent operate under a catastrophic mathematical assumption.
The assumption of independence.
Right. OAT assumes that parameters are strictly additive. It inherently believes that the optimal state of parameter A operates in a vacuum, entirely unaffected by the state of parameter B.
And to be fair, additive parameters do exist in trading.
Give me an example of an additive parameter.
Sure, so if parameter A defines the threshold for initiating a long position, and parameter B defines the threshold for initiating a short position, those logic trees never overlap.
Right, because a trade can't be simultaneously long and short.
Exactly. Tweaking the short criteria does not mathematically alter the efficacy of the long criteria. So for strictly additive parameters, OAT actually works perfectly.
But the reality of modern quantitative architecture is that parameters are rarely independent.
Rarely, they are deeply inherently coupled. And the author provides a textbook example of this using multi-time frame confirmation logic.
Okay, let's walk through that. Imagine a strategy governed by a higher time frame entry threshold, so HTF, and a middle time frame entry threshold, the MTF.
The higher time frame acts as a preliminary filter. It dictates which market regimes or setups are even passed down to the middle time frame for execution analysis.
Which means the parameters are fundamentally interactive.
Highly interactive. If you alter the HDF threshold, you completely change the distribution of data that the MTF threshold receives.
Right. So the optimum MTF value under a strict HTF filter is going to be drastically different than the optimum MTF value under a loose HTF filter. The source text actually includes a precise data table to illustrate this failure mode. Let's look at the interaction between HTF entry cell and MTF entry cell.
Okay.
So in an OAT sweep, the algorithm freezes the MTF parameter at its default. Let's say it's 0.01. It then tests the HTF values.
Right, and when HTF is set to 0.02, while MTF remains frozen at 0.01, the strategy yields a profit of plus 42%.
Okay, pretty good.
But when HTF is increased to 0.03, again with MTF frozen at 0.01, the profit drops to plus 35%.
So the OAT logic looks at those two discrete data points, determines that 42% is superior to 35%, locks HTF at 0.02, and just marches forward.
Yep. It discards the 0.03 value entirely.
But the table in the text reveals the fatal flaw. Because if the algorithm had tested the specific combination of HTF at 0.03 and MTF at 0.02, the P&L leads to a global optimum of plus 51%.
And OAT is structurally blind to that 51% peak.
Because it locked MTF at the default 0.01, the HTF value of 0.03 just appeared suboptimal.
It evaluated the parameters in isolation. It completely missed the synergy of their interaction. In optimization, we call this getting trapped in a local optimum.
It's like, okay, think of it like navigating a mountain range. But you're wearing a mechanism that only allows you to step perfectly north or perfectly east.
That's a great analogy. You can never step diagonally.
Right. So you walk perfectly north until the elevation starts dropping. Then you walk perfectly east until the elevation drops again.
Yeah.
And you declare you've reached the summit.
Completely unaware that a massive diagonal ridgeline just 50 feet away leads to the true peak of the mountain.
Exactly. You are standing on a foothill celebrating.
The author actually formalizes this blindfolded mountain climber analogy using the Hessian matrix and cross derivatives.
Which is the mathematical proof of why OAT fails.
Yeah.
I really want to dig into that calculus because understanding the Hessian matrix feels like, I don't know, the skeleton key to understanding optimization topologies.
It really is. I mean, in a simple single variable function, the first derivative gives us the slope, and the second derivative tells us the curvature, like whether the slope is increasing or decreasing.
Right, basic calc. But we are in a multidimensional space here.
Exactly. When navigating a multidimensional objective function, where the output is P&L and the inputs are your 12 parameters, the Hessian matrix is a square matrix containing all the second-order partial derivatives of that function.
Okay, so it describes the local curvature of the entire P&L landscape.
Yes. And the critical components here are the off-diagonal elements of the matrix, the mixed partial derivatives or cross derivative.
Cross derivatives. Okay, what do those actually measure?
A cross derivative measures the rate of change of the slope in the x direction as you move in the y direction.
So in plain terms, it asks, if I change parameter b, how does that alter the optimal trajectory for parameter a?
Precisely. If parameter a and b are totally independent, changing b does nothing to a's slope. The cross derivative just evaluates to 0.
But if the parameters are coupled, like our timeframe filters, changing the higher timeframe fundamentally alters the slope of the middle timeframe.
Right. The cross derivative is non-zero.
And when cross derivatives are significant, the objective function landscape warps.
The axes are no longer orthogonal regarding their optimal paths. The landscape literally forms diagonal ridges or diagonal valleys.
And OAT, by definition, optimizes along orthogonal axes. Perfectly north, perfectly east.
It is mathematically incapable of traversing a diagonal ridge. If the true global optimum lies along a trajectory defined by strong cross derivatives, OAT is guaranteed to fail.
That is a chilling realization for anyone running standard multipath sweeps on complex strategies. You are systematically filtering out your best possible performance.
You're leaving alpha on the table because your map is broken.
So if grid search takes centuries and OAT is mathematically blind to the real peaks, we need a paradigm shift in how we search.
We need an algorithm that can map the off-diagonal elements, evaluate parameters simultaneously, and do it within a feasible compute budget.
Which leads directly into the core solution of the text: Bayesian optimization.
Yes. We are abandoning rigid, predefined search paths and moving into probabilistic mapping.
Right. Bayesian optimization essentially acts as an algorithmic cartographer. Like, instead of blindly testing points hoping to hit the summit, it uses initial random tests to build a surrogate model of the entire landscape.
And this surrogate model is just a mathematical approximation of the true, highly complex objective function.
Because the true function, like running the actual backtest, is computationally expensive.
Very expensive. But the surrogate model is incredibly cheap to evaluate. You initialize the process by running a small batch of completely random parameter combinations and recording their PNL.
You drop 10 random pins across the map and record their altitudes.
Exactly. And using those 10 data points, the algorithm calculates a probabilistic surface that estimates what the rest of the unmapped mountain range looks like.
That's the surrogate.
That's the surrogate. But the true brilliance of Bayesian optimization lies in what it does next, using what's called an acquisition function.
Okay, the acquisition function essentially queries the surrogate model, right? It looks for the absolute best place to drop the 11th pin.
Right. It calculates expected improvement. The algorithm evaluates the rough map and balances two competing directives: exploitation and exploration.
Define those in this context.
Sure. Exploitation means testing points very close to the highest known peaks, trying to just inch upward.
Like trying to find the very tip of the hill you're already on.
Exactly. Exploration, on the other hand, means testing vast, unmapped regions where the uncertainty is high on the chance that an entirely undiscovered, much larger mountain exists over there.
Okay, so the acquisition function mathematically calculates the exact coordinate that offers the highest expected value based on that balance.
Yes, it tests that coordinate, runs the heavy backtest to get the true PNL, feeds that ground truth data back into the algorithm, and recalculates the surrogate model.
So the map gets sharper with every single iteration.
Much sharper, and specifically focusing its resolution on the most promising areas.
And because it maps the space holistically, it effortlessly identifies and traverses those diagonal ridges driven by cross derivatives.
It sees the diagonal paths that OAT is blind to. And the specific engine the author utilizes for this is the Optuna framework, and its default algorithmic sampler is the tree-structured Parson estimator, or TPE.
TPE. Tree-structured Parson estimator. It sounds computationally heavy, but if I'm understanding the source correctly, it's actually just doing probability distribution matching between sets of good results and bad results.
You're hitting on the exact core mechanism. Standard Bayesian approaches model the probability of the output given the inputs. But TPE flips Day's theorem on its head.
Okay.
It models the probability of the inputs given the output.
Walk me through that inversion. How does it do that?
As TPE runs iterations, it maintains a dynamic threshold. Every parameter combination that yields a PNL above that threshold is bucketed into a subset we can call the success group.
Okay, and everything below the threshold goes into the failure group.
Exactly. So it splits the historical data into two distinct piles. Then it uses kernel density estimation to build a probability density function for the parameters in the success group.
Okay, so it mathematically defines the shape of a successful parameter combination.
Yes. The text denotes this distribution as lel of theta, and then it builds a separate density function for the failure group, denoted as li of theta.
So instead of plotting a complex 3D surface map, it's really just comparing two statistical profiles.
Exactly.
He basically says, hey, successful strategies tend to have HTF values clustered around 0.03 and MTF values clustered around 0.02, and failures tend to cluster elsewhere.
That is exactly what it does. When the acquisition function looks for the next point to test, it evaluates potential parameter combinations by maximizing the ratio of therophi divided by divider dollars.
It actively hunts for coordinates that have a massive probability of belonging to the success distribution and a near-zero probability of belonging to the failure distribution.
It's incredibly elegant, and the efficiency gains here are just breathtaking. The author states that for a 12-parameter search space, TPE generally converges on the global optimum within roughly 500 iterations.
Let's run the math on that. If our Parquet cache backtest runs in 0.1 seconds, 500 iterations takes exactly 50 seconds.
50 seconds to map the multidimensional space, analyze the cross derivatives, and locate the synergistic global peak that OAT missed.
50 seconds compared to 895 years for the grid search.
It is one of the most profound examples of algorithmic leverage in modern data science.
It's unbelievable. But Optuna is a framework, right? A toolkit. TPE is the default tool, but the author dedicates significant real estate to evaluating other algorithmic samplers.
Because deploying the right sampler for the right mathematical environment is critical.
Right. Let's break down the alternatives, starting with the CMAES sampler, covariance matrix adaptation evolution strategy.
CMAES abandons the surrogate probability model entirely and utilizes an evolutionary paradigm. It doesn't look at the history of every point tested. It only looks at the current generation of points.
Like biological survival of the fittest, but applied to P&L.
Precisely. The algorithm generates a population of, say, 50 parameter combinations. It tests them all. It discards the worst performers and uses the best performers to breed the next generation of 50 points.
And where does the covariance matrix adaptation part come in?
That's the magic. The matrix defines a multivariate normal distribution. Think of it as an n-dimensional ellipse that dictates where the next generation will be spawned.
So if the surviving parameters from generation 1 form a diagonal line across the landscape, the covariance matrix physically stretches the search ellipse along that exact diagonal axis for generation 2.
It actively mutates its search distribution to match the shape of the objective function. If your 12 parameters are deeply coupled with intense cross derivatives, CMAES is an absolute powerhouse.
Because it zeroes in on complex interactions faster than almost any other method.
It does, but the author notes some very specific limitations.
Like what?
It cannot handle categorical variables.
Discrete choices.
Right, like choosing between moving average type A or type B. It requires continuous numerical landscapes to calculate covariance. And it has a warm-up cost.
Because it relies on generational adaptation, the first few generations are effectively random.
Exactly. The author notes it often requires 200 to 2,000 iterations to build enough evolutionary momentum to surpass TPE.
So if your compute budget is only 100 runs, CMAES will heavily underperform.
It will. And that computational budget constraint brings us perfectly to the next tool, the Gaussian Process Sampler, or GP.
This is the classic heavily mathematical implementation of Bayesian optimization, right?
Yes. Gaussian processes map the landscape using a multivariate Gaussian distribution defined by a mean function and a covariance kernel, often a Mattern or radial basis function kernel.
Okay, that sounds intense. What sets it apart practically?
What sets GP apart is its rigorous quantification of uncertainty.
So the acquisition function isn't just looking at the highest predicted P&L, it's evaluating the exact confidence interval of that prediction.
Exactly. TPE just models the distributions of good versus bad inputs. GP models the actual continuous surface of the objective function and explicitly calculates the variance, the uncertainty, at every single unmapped coordinate.
Which makes its acquisition function incredibly efficient at balancing exploration and exploitation.
Yes. GP can often find a global optimum in just 50 to 100 backtest runs.
It extracts the maximum possible theoretical insight from every single data point.
It really does.
So why isn't it the default? Why use TPE over GP if GP is so efficient?
Because of the matrix inversion bottleneck.
Okay.
To update the multivariate Gaussian distribution, the algorithm must invert an annuller times non-matrix, where nullers is the number of points tested so far, and the computational complexity of matrix inversion scales at big O of n cubed.
Oh. Meaning as the number of tested points grows, the time it takes the algorithm to think about the next point just completely explodes.
By iteration 200, the Gaussian process algorithm itself might take 30 seconds just to calculate the next coordinate to test.
Wow. And if your underlying backtest only takes 0.1 seconds, thanks to the Parquet cache.
You are spending 99% of your compute time waiting for the optimizer to do math, rather than actually running backtests.
Right, so GP is the heavy artillery you deploy only when your backtests are agonizingly slow.
Exactly. If a single run takes an hour because you're running tick-level order book simulations, you only have the budget for maybe 50 runs. You want GP wringing every drop of probabilistic insight out of those 50 evaluations.
But for cached high-speed backtests, TPC scales infinitely better because its KDE calculations are essentially big O of n.
Yep, it's much faster computationally. The author also rounds out the toolkit by discussing baseline samplers, random search in Quasi-Monte Carlo, or QMC.
Well, random search is pretty self-explanatory, but QMC utilizes low discrepancy sequences like Sobel or Halton sequences. What is the mechanical difference between a pseudo-random number generator and a Sobel sequence in this context?
So, a standard random number generator is prone to clumping.
Clumping.
Yeah, if you drop 100 random pins on a map, you will inevitably have clusters of pins in one quadrant and massive unexplored voids in another. It's not evenly distributed.
Okay.
So Bessel sequences, however, are deterministic mathematical series designed to fill an n-dimensional space as uniformly as possible. They actively repel each other.
Ah, so they guarantee an even distribution of test points across the entire parameter matrix.
Exactly. But because QMC doesn't adapt to the results, it doesn't learn from the P&L, it's really only used as a primer.
The text actually recommends using QMC for the initial startup iterations, right?
Right. Before you unleash TPE to start building probability densities, you feed it 50 or 100 QMC-generated points to ensure its baseline map has 0 structural blind spots.
The author provides a brilliant empirical benchmark, actually pitting these samplers against each other on the 12-parameter strategy. And the scoreboard perfectly validates all the underlying calculus we just talked about.
It's a great visual.
TPE takes the gold, hitting a maximum PNL of roughly 51% around iteration 180, maintaining incredibly low computational overhead.
CMAES secures second place, converging on a 49% PNL, but it required around 250 iterations to evolve its covariance matrix to that point.
Right, and GP spikes rapidly, finding a 48% PNL by iteration 90, which just demonstrates its massive sample efficiency.
But true to form, its calculation times become heavily prohibitive past that 200 iteration mark.
And the baselines just totally validate the need for smart search. Random search tops out at 42%, taking 270 iterations to blindly stumble into it. QMC hits 43% around iteration 200.
What's fascinating here is the delta between random search's 42% and TP's 51%. That is pure algorithmic alpha.
It's a 20% relative increase in yield, generated entirely by using a superior mathematical compass to navigate the exact same search space.
Exactly.
Wait, so you're saying my infrastructure ultimately dictates my math? Like if my underlying backtest logic is unoptimized and takes a full minute to execute, I literally cannot afford to use CMAES because 2,000 iterations would take a day and a half.
Yes. You'd be forced to use OAT or a tiny GP run.
So the Parquet cache isn't just a time-saving convenience. It is literally the key that unlocks higher-order algorithms.
That is the defining realization of quantitative architecture. Speed is not a luxury. Speed is what buys you the statistical sample size necessary to utilize advanced optimization logic.
Okay, so we've established that Bayesian optimization, specifically TPE, can find the absolute highest peak on the multidimensional mountain, the parameter combination yielding that 51% PNL.
We have.
But the author introduces a massive paradigm shift in the next section. What if maximizing the objective function hunting for the highest PNL is fundamentally the wrong goal?
We transition here from data science theory into the vicious reality of market mechanics.
Right.
The author states emphatically that running Optuna with a single objective to maximize PNL is a guaranteed path to account liquidation.
And the culprit is lost profit asymmetry.
Exactly. If an algorithm is told to strictly maximize profit, it will push parameters to their absolute razor's edge.
It will tighten moving average lookbacks to trigger earlier entries, widen stop losses to prevent premature exits, and crank leverage.
It will generate a massive theoretical P&L, but it will inevitably expose the equity curve to devastating drawdowns.
Because the algorithm does not understand capital preservation unless it's explicitly programmed to.
Right. If you suffer a 10% drawdown, you require an 11% gain to recover. But if the algorithm's aggressive parameters trigger a 50% drawdown, you require a 100% gain just to return to parity.
So an optimizer that finds a strategy with plus 80% P&L and negative 40% maximum drawdown has just delivered a mathematically toxic asset.
Yes, so we cannot feed Optuna a singular scalar value. We have to transform the process into multi-objective optimization.
We instruct the algorithm. Maximize P&L, A and D, minimize maximum drawdown simultaneously.
Which creates an immediate mathematical contradiction.
Because risk and reward are intrinsically tethered.
Exactly. The exact parameter shifts that increase overall yield, higher frequency trading, wider stops, are the identical parameter shifts that deepen the drawdown potential. They are competing objectives.
So in a single objective search, the output is the one coordinate with the highest peak. But if there is no singular coordinate that perfectly maximizes profit and perfectly minimizes risk, how does the TPE algorithm present the solution?
The output transforms from a single point into a curve, known in multi-objective calculus as the Pareto front. Optuna utilizes genetic algorithms like NSGAI, non-dominated sorting genetic algorithm, to map this front.
Okay, how does NSGAI actually define what gets to be on that curve? What is non-dominated sorting?
The algorithm evaluates the population of parameter sets and ranks them. A parameter combination is non-dominated if there's no other combination in the entire set that is better in both objectives.
So if strategy X has 50% P&L and 5% drawdown, and strategy Y has 60% P&L but 8% drawdown.
Neither dominates the other. One is better on profit, the other is better on risk. They both sit on the Pareto front.
I see. But if strategy Z has 40% P&L and 10% drawdown, strategy X dominates it completely. Higher profit, lower risk.
Exactly. Strategy Z is discarded. The Pareto front is the absolute outer boundary of efficiency. It maps the trade-off curve where improving one metric strictly requires sacrificing the other.
The author provides a staggering case study to illustrate how a quantitative trader actually selects a point along this Pareto front. They present 3 hypothetical strategies outputted by the algorithm: strategy A, strategy B, and strategy C.
Let's analyze the math here, starting with strategy C, which represents the extreme profit objective.
Okay, strategy C outputs a massive base P&L of plus 300%. The raw yield is incredible.
However, because it sits on the extreme end of the Pareto curve, its maximum drawdown is equally extreme at 17%.
A 17% drop in equity. In a vacuum, maybe a trader stomachs that for a 300% gain. But quantitative strategies are built to be leveraged. We have to map that drawdown against liquidation thresholds.
Exactly. If you apply 10x leverage to a strategy with a 17% baseline drawdown, you suffer 170% loss. You are instantly liquidated by the exchange.
It's game over.
The author calculates that to survive a 17% structural drawdown with a safe buffer, your absolute maximum theoretical leverage is roughly 3x.
So 300% base P&L multiplied by 3x leverage yields a leveraged return of 900%. A formidable result. But let's contrast that with strategy A, which sits on the opposite, low-risk end of the Pareto front.
Right, strategy A only outputs a base P&L of 55%.
But the maximum drawdown for strategy A is an astonishingly low 0.9%.
Less than a 1% drop, which radically alters the leverage calculus.
Because the drawdown variance is so incredibly tight, the capital efficiency skyrockets. The author calculates that a 0.9% maximum drawdown can safely support up to 55x levered without risking liquidation.
Right, so 55% base P&L multiplied by 55x leverage results in a leveraged return of 3,025%.
The low-risk strategy, which appeared dramatically inferior on a base P&L level, generates over 3 times the absolute capital of the high-risk strategy, simply because its stable equity curve unlocks efficient leverage.
Strategy A mathematically dominates strategy C when leverage constraints are applied. But the author introduces strategy B to complicate the calculus even further.
Strategy B sits somewhere in the middle. Its base P&L is only 25%, the lowest of the 3. Its maximum drawdown is 0.75%, allowing for 66x leverage. The final leveraged return calculates to 1,650%.
So strategy A makes 3,025% and strategy B makes 1,650%. By all conventional logic, strategy A is the superior asset.
Right. Why would a quantitative trader ever look at strategy B if it makes half the money?
This is where the author introduces a critical, often ignored metric, effective score, or P&L weighted by active time. We have to evaluate the time and market column.
Oh, right.
Strategy A generates its return by being actively engaged in trades 15% of the time. Strategy B generates its 1,650% return while only being active 5% of the time.
I see the mechanism here. Strategy B is immensely capital efficient regarding time.
It leaves your portfolio capital completely unencumbered 95% of the time. A sophisticated algorithmic firm doesn't run one strategy, they run an ensemble.
So you could take the capital freed up by strategy B and deploy it across 3 or 4 other uncorrelated strategies during that 95% downtime.
Exactly, drastically multiplying overall portfolio yield and reducing global portfolio variance.
The highest absolute integer outputted by Optuna is rarely the optimal real-world asset. We have to filter the Pareto front through leverage, liquidation math, and temporal capital efficiency.
We do, but the author drops one final heavy caveat regarding these massive theoretical leverage numbers.
Yes, the funding rates. Running 55x leverage on a perpetual futures contract incurs staggering funding rates. On exchanges like Binance, funding is calculated and extracted every 8 hours.
If you are paying 0.01% per epoch, that is 0.03% daily.
Multiply by 55x leverage, you are bleeding 1.65% of your total account equity every single day in sheer funding fees to maintain the position.
If a trade remains open for a week, you lose 11% to fees, completely destroying the 0.9% maximum drawdown constraint.
So the Pareto front provides a map, but the trader must still superimpose the physics of market microstructure fees, slippage, and funding over that map.
Exactly.
So we have built the Bayesian surrogate model, we've navigated the multi-objective Pareto front, and we've accounted for market physics. How do we visualize this architecture? Staring at CSV outputs of thousands of NSGA2 iterations is meaningless. How do we confirm our logic visually?
Optuna provides natively integrated visualization libraries, and the most critical tool for analyzing parameter interactions is the contour plot.
A contour plot functions exactly like a topographical map for a hiker, mapping elevation. But here, the x and y axes represent 2 specific parameters, and the elevation, the colors in contour rings, represents the resulting P&L.
The contour plot provides instant visual proof of the Hessian matrix cross-derivatives we discussed earlier.
You just look at the isolines, the rings indicating changes in elevation.
If the isolines form perfect horizontal or vertical bands parallel to the axes, the parameters are completely independent.
The mountain goes straight north or straight east. Changing the y parameter has 0 impact on the optimal location of the x parameter. The cross derivative is 0.
In that specific visual scenario, an OAT sweep would have performed flawlessly. But if the isolines form a diagonal ellipse or a slanted ridge, you are looking at visual confirmation of parameter coupling.
The optimal x value dynamically shifts based on the y value. It proves, without a shadow of a doubt, that OAT would fail and Bayesian optimization was necessary.
The contour plots also reveal the stability of the optimum. The author aggressively warns against selecting parameters that form a sharp, jagged peak on the contour map. We want to find a plateau.
Why is a flat, broad elevation superior to the absolute highest mathematical spike?
Because a jagged spike indicates extreme fragility. It represents a parameter coordinate that is hyper-optimized to the exact idiosyncratic noise of the historical dataset.
Right. So if market volatility shifts by even a fraction of a percent in live trading, you fall off the spike and P&L plummets.
The trace of the Hessian matrix at that peak would be massive, indicating extreme curvature and sensitivity.
Exactly. A plateau, however, indicates robustness. It is a broad region where minor variations in parameter values, or minor variations in live market data, have negligible impact on the overall P&L. The objective function is stable.
Selecting a point on a plateau is your first line of defense against the ultimate enemy of optimization, overfitting.
Before we tackle overfitting, there's one more visualization tool. Parameter importance, typically calculated using the FANOVA algorithm.
FANOVI, functional analysis of variance. It evaluates the surrogate model and assigns a fractional importance score to each parameter. It tells you which dials actually move the needle and which ones were just spinning freely.
The author suggests that if the parameter score is below 0.01 in importance, you can permanently freeze it at a default value, stripping a dimension from your search space and exponentially accelerating future optimization runs.
But there's a trap there, isn't there?
A significant one. A parameter might exhibit near zero importance when evaluated in isolation, but exert massive influence through a high-order interaction with another parameter.
You must cross-reference low FANOVA scores against the contour plots to ensure you aren't deleting a parameter that serves as a critical coupled variable.
Taking all of this, the speed of OAT, the depth of TPE, the FANOVA analysis, the author synthesizes a hybrid workflow. They don't advocate for using Bayesian optimization on every single variable blindly. They construct an architectural pipeline.
It is the approach of a seasoned engineer. Step 1 is manual classification. You utilize your domain knowledge of the strategy's logic to partition the 12 parameters into 2 distinct sets: the strictly additive parameters and the coupled parameters.
Right. Like you know that the moving average look back for a long position and the look back for a short position never intersect. They are additive, but the higher time frame and lower time frame threshold filters are deeply coupled.
Step 2. You execute a rapid OAT sweep exclusively on the additive parameters. Because cross derivatives are 0, OAT finds their optimal baseline perfectly in a matter of seconds.
Step 3. You lock those additive parameters in place. You have reduced your search space from 12 dimensions down to, say, 6 dimensions. Now you unleash Optuna and the TPE sampler exclusively on the 6 coupled parameters.
By structurally reducing K, the number of parameters, you collapse the computational volume of the space. TPE can build a radically more accurate surrogate model of a 6-dimensional space in 300 iterations than it ever could in a 12-dimensional space.
You achieve maximum precision with minimal compute budget.
It is a phenomenal synthesis. But we have to address the elephant in the room, which we touched on with the contour plateaus: overfitting.
If I run TPE for 600 iterations, probing the historical data over and over, identifying the absolute perfect multi-dimensional ridge, aren't I virtually guaranteed to find a parameter matrix that simply memorized the past?
In statistics, this is known as the multiple comparisons problem, and it is the terminal disease of algorithmic trading.
Right, if you simulate a million random coin-flipping monkeys, one of them will flip heads 20 times in a row. They don't have alpha, you just ran too many tests.
Exactly. The more iterations Optuna runs, the higher the probability that the resulting plateau is just a statistical ghost born of historical noise.
So if a static 70-30 split is vulnerable to regime changes like training on a bull market and testing on a bear market, how does walk-forward optimization actually fix that? Are we anchoring the start date and expanding the window, or is the whole training window rolling forward through time?
Walk-forward optimization utilizes an unanchored rolling window, and it is the gold standard for proving robustness. You do not train on 70% of the data and test on 30%.
Okay, what do you do?
You train Optuna on, for example, a 6-month window, January to June. You lock the parameters, and you run a strict out-of-sample test on July.
You record July's P&L.
Then you roll the entire window forward. You train Optuna on February through July, you test on August, you repeat this process across your entire multi-year data set, stitching together the out-of-sample months to create a contiguous equity curve.
If the strategy is overfitted, if it just memorized January through June, it will collapse in July. If the walk-forward equity curve remains profitable, it proves the Bayesian optimizer is actually identifying structural market inefficiencies, not just statistical noise.
To compound that defense, you employ Monte Carlo permutations. You take the series of trades generated by the walk-forward test, and you scramble the sequence.
How does scrambling the sequence of historical trades validate the parameters?
Because it tests for a sequence of returns risk. If your P&L only survived because you happen to hit 5 massive winning trades right before a 20% drawdown, your parameters are fragile.
By randomly permuting the trade order 10,000 times, you map the true probability distribution of your maximum drawdown.
Right. If the 99th percentile Monte Carlo drawdown exceeds your liquidation threshold, you discard the parameters, regardless of the baseline P&L.
The author provides a final mathematical heuristic regarding the iteration budget itself, essentially establishing a Bonferroni correction for Bayesian search. How many iterations should we run to map the space without crossing the threshold into data mining?
The heuristic is tied directly to the dimensionality. The absolute minimum budget is 10 times K, where K is the number of parameters.
For our 12-parameter strategy, 120 iterations is the bare minimum required for T2E to initialize the KDE distributions and build a functional surrogate map.
And the optimal zone. The optimal target is 30 times K to 50 times K, so 360 to 600 iterations.
This provides sufficient budget for the acquisition function to balance exploration and exploitation, mapping the diagonal ridges without oversaturating the dataset and triggering the multiple comparisons problem.
Exactly.
So what does this all mean? We've journeyed from the sheer physics of compute limitations, where a naive grid search demands 8,950 years, to the elegance of probability distribution mapping.
We dissected the OAT sweep, realizing that while its linear scaling is fast, its mathematical inability to calculate cross-derivatives leaves traders stranded on false summits.
We observed how Bayesian models, specifically tree-structured Parson estimators, utilize surrogate mapping and expected improvement acquisition functions to navigate multidimensional interactions in seconds.
We analyzed the covariance matrices of CMA-ES and the variance tracking of Gaussian processes.
We confronted the reality of loss-profit asymmetry, transforming singular optimization into the multi-objective mapping of the Pareto front, filtering theoretical returns through the harsh physics of leverage, funding rates, and active time efficiency.
And finally, we engineered a hybrid workflow, validating our logic through contour plateaus and defending against statistical ghosts through unanchored walk-forward permutations.
The frameworks exist. Libraries like Optuna are readily available. The bottleneck is no longer hardware. It is the trader's understanding of the mathematical topology they are attempting to conquer.
Which raises a fascinating philosophical parallel. We've spent this whole time detailing how artificial intelligence navigates complex, coupled parameters to optimize an objective. But if we map this logic onto human behavior, we almost exclusively utilize OAT.
That is an incredible pivot. Break that down.
When humans attempt self-optimization, we isolate variables. You decide to improve your health, so you change your diet. One axis, perfectly north. You decide to improve your productivity, so you alter your sleep schedule. Perfectly east. We assume our habits are strictly additive.
But biological and psychological systems are deeply intrinsically coupled.
Exactly. What if the optimal state of human performance lies on a diagonal ridge? What if the efficacy of your diet is fundamentally cross-derivative to your sleep schedule, your stress levels, and your environment?
By optimizing one habit at a time and locking it in, we guarantee that we remain trapped in local, suboptimal foothills.
We lack the cognitive capacity to build a Bayesian surrogate model of our own existence. We are blind to the multidimensional interactions that define our true potential. Perhaps the algorithms possess a clarity regarding complex systems that we have yet to grasp.
We are optimizing our lives one parameter at a time, completely oblivious to the diagonal ridges we walk right past. That is a profoundly haunting concept to end on, something to evaluate while your Parquet-cached backtests compile. Analyze the cross-derivatives in your code, and perhaps analyze the cross-derivatives in your own routines. Thank you for joining us on this deep dive into the architecture of optimization. We will catch you on the next one.